for analyzing the Capstone Challenge for grade 11 STEM students. This comes from the Egyptian Ministry of Education's Central Unit for Gifted and Talented Students, and it's for Semester 2, 2025-2026.
And it is a heavy document. I mean, I've read technical briefs for actual startups that were less detailed than this. It's titled Engineering the Living System.
Right.
And honestly, if you handed this to a second-year university engineering student, they might sweat a little.
The premise is just absolutely wild. We aren't bubbling in Scantron sheets here. The students have to build a fully automated closed-loop life support system for either fish or plants or a hybrid of both.
An aquaponics system.
But here's the kicker, the part that really sets the tone. They have to build the physical structure, the body of the machine, using Crash.
Waste materials, to be precise.
Yeah.
It's high-tech silicon chips meeting the recycling bin.
So just picture this for a second. You've got microchips, these delicate sensors, complex code, all exploring the complexities of biological life.
And it's all held together by, what, old plastic bottles, scrap wood, maybe some duct tape.
So before we get into the wiring and the code, let's just zoom out. Why this specific project? Why are we asking 16-year-olds to solve food security problems with garbage?
That's really the right place to start. I mean, context is everything here. The document explicitly anchors this project in what they call Egypt's Grand Challenges. So this isn't learning for the sake of learning. It's mission-oriented. It's telling these students, hey, your education has a direct purpose.
I saw that list of challenges in the intro. It is daunting. It reads like a list of things that keep world leaders up at night.
It really does. They list 4 key national priorities. 1, increasing the industrial and agricultural base.
Okay.
2, recycling waste for economic value. 3, managing population growth. And 4, reducing pollution.
It's interesting how those 4 interact, isn't it? Because usually when you have massive population growth, you end up with more pollution and less agricultural land because you're building cities on top of farms.
Exactly. And that's the tension the students have to solve. They're being asked to break that cycle. The essential question the document poses is, how can automated feedback systems maintain environmental conditions to support production across diverse regional contexts?
That phrase, diverse regional context, really stuck out to me. It implies they aren't just building a lab experiment that only works in, perfect air conditioning.
No, not at all.
They're prototyping something that needs to work in the desert, or maybe in the humid delta, or on a scorching rooftop in Cairo.
Precisely. The logic is, if you can automate agriculture, if you can turn a farm into a smart machine that monitors itself, you can drastically increase efficiency. You use less water, less fertilizer.
And you can scale it up to feed that growing population without destroying the environment.
That's the goal.
So the students are effectively acting as chief technology officers for a startup that's tackling the apocalypse.
It's a dramatic way to put it, but yeah, it's pretty accurate. They're engineering resilience.
Okay, let's get into the machine itself. The document talks about a closed-loop feedback control system. Now, to the layperson, that just sounds like buzzword soup.
It does sound like consultant speak.
Right. But this is actually a very specific engineering concept, isn't it?
Oh, absolutely. It is the fundamental concept of modern automation. Just think of it as a continuous cycle of awareness and action. The source even provides a schematic scheme 1 that breaks it down.
Okay.
It starts with the desired set point.
So that's the goal. Like, I want the water in my fish tank to be exactly 25 degrees Celsius.
Right, that's your target. Then you have the sensors. These are the eyes of the system. They look at the actual world and say, hey, wait a minute, the water is actually 20 degrees.
So there's a gap. Reality doesn't match the goal. The system is failing.
And that's where the controller comes in. This is the brain. Usually a microcontroller like an Arduino or an ESP32, which the students themselves have to program.
Okay.
It takes that sensor data, compares it to set point, and it calculates the error. It realizes we have a problem. We are 5 degrees too cold.
And then, you can't just worry about it. It has to do something.
And that is the actuator. The actuator is the muscle. It's the heater. It's a pump, a fan, a little motor. The controller sends a signal to the actuator, in this case, the heater, to turn on.
So the heater warms the water.
The heater warms the water, the sensor sees the temperature rise, reports back to the controller, and when it finally hits 25, the controller tells the heater, okay, stop.
And that loop just runs forever.
Measure, compare, act, and repeat. That's a closed loop. It sounds simple, like a thermostat in your house.
But a thermostat you buy at the hardware store is a finished product. You just screw it to the wall and walk away.
Yeah.
These students have to build the brain, wire the entire nervous system, and attach the muscles themselves.
And if they get the wiring wrong.
Nothing happens.
Yeah.
Or worse, you see smoke.
Exactly. And they have to do all this within extremely tight physical constraints. This brings us to the design challenge section. They're not building a full-size greenhouse in the schoolyard.
No, this is a desktop prototype. I saw the numbers. If they choose aquaculture fish farming, the tank is a maximum of 10 liters.
Which is tiny.
It's barely 2 large milk jugs.
And for crops, the growing area is just 0.25 square meters, the microfarm. But here's the thing. The small scale actually makes it harder in some ways.
Really, I would have assumed smaller is easier. Fewer materials, less to go wrong.
Not for the physics of the environment. See, small bodies of water fluctuate in temperature much, much faster than large ones. If the AC in the room turns off, or even a cloud passes over the sun, that 10-liter tank changes temperature very rapidly. A large lake is stable, a bucket is volatile.
So the system has to be incredibly responsive to catch those changes.
And it has to run completely solo. The rule is continuous operation for at least 6 hours without human intervention.
That is the stress test. It's the set it and forget it standard. If a pipe leaks, if the soil dries out, the student cannot touch it.
No, they have to stand back, hands in their pockets, and just watch. The code has to handle it.
Speaking of handling it, I really want to get into the sensor requirement. It's requirement number 3.
Yeah.
This feels like the teacher sat down and said, how can we make this really, really difficult?
Oh, the controlled variables rule. I think it's brilliant pedagogy.
Okay, so they have to monitor 3 environmental parameters. But the document says, and I'm quoting here, only one is permitted to be temperature, pH, or salinity.
Right. And in the world of DIY electronics, those 3, temperature, pH, and salinity, are kind of the hello world of sensors.
They're the easy ones.
They're cheap. They're often waterproof. The code is basically copy-paste easy. Everyone knows how to read a digital thermometer.
So by capping it at 1, they're forcing the students into the deep end. They're saying, okay, you get 1 easy pass.
Okay.
For the other 2, you have to work for.
Exactly.
So if I use my 1 easy pass on, say, temperature, what else is left? What are these students being forced to measure?
Well, this is where the biology knowledge has to merge with the engineering. If you're growing plants, maybe you need to measure soil moisture, but not just a simple wet or dry check. You might need capacitive moisture sensors that give you a specific percentage reading and don't corrode in the soil.
What else?
Or maybe light intensity measuring lux to make sure you're optimizing for photosynthesis.
And what about for the fish?
That's even harder. They might need to look at dissolved oxygen. That is a crucial metric for fish health. If the oxygen drops, the fish suffocate. But measuring it electronically requires a specialized probe. Or turbidity, how cloudy the water is. Or ammonia levels, which can require very specific and often expensive or finicky electrochemical sensors.
So they have to actually understand the chemistry of what they're measuring, not just plug in a wire. They have to know why ammonia even matters.
Precisely. And remember, they have to control these variables. The document requires at least 2 functional actuators.
So I'm measuring soil moisture and it gets too dry. I need a pump. That's my actuator.
Yes. But think about the engineering chain there. A microcontroller, the brain, it operates at a very low voltage, usually 3.3 or 5 volts.
Right.
A water pump usually needs 12 volts or more to actually move water. You can't just plug the pump into the computer chip.
You fry the brain.
Instantly. It's like trying to power a blender with a watch battery.
Or worse, trying to power a blender by plugging it into your smartphone. It destroys the phone.
Exactly. So the students need to learn about relays or MOSFETs or motor drivers. They have to build a power distribution circuit that separates the high voltage muscles from the low voltage brain. That's real electrical engineering.
And then you have the code itself, the control algorithm. The document lists a few options here. On-off control, rule-based logic, or adaptive control. Can we break those down? On-off seems pretty obvious.
On-off is the simplest. If temp is less than 20, turn heater on. It's a light switch, but it has a big problem called chatter.
Chatter. Like it talks too much.
No, like it jitters. Imagine the water is at 19.9 degrees. The heater turns on. A second later, it hits 20.0. The heater turns off.
Oh, I see.
It immediately drops back to 19.9. The heater turns on again. It just clicks on and off 5 times a second. That will burn out your relay and destroy your equipment.
So you need some kind of buffer zone.
You need something called hysteresis. That's an engineering concept where you say, turn on at 19, but don't turn off until it reaches 21. It creates a safe range so the machine isn't panicking.
And teaching a 16-year-old to code hysteresis to a C++ loop, That's a significant step up from basic logic.
And that's the simple version. The document also mentions adaptive control. That starts to sound a little like AI.
It does.
It's the grandfather of AI, really. Adaptive control implies the system can modulate its behavior. For example, proportional control. If the temperature is way off, say it's freezing, you turn the heater on at 100% power.
Okay.
But if it's only 1 degree off, you don't blast it. You run the heater at, say, 10% power so you don't overshoot the target.
Ah, that requires pulse width modulation, right? Rapidly switching the power on and off to simulate a lower voltage.
It does. It requires modulating the energy output, not just flipping a switch. I mean, if a student group pulls off a full PID controller proportional integral derivative for this project, they are basically ready for industrial internships.
Wow.
That is the standard used in oil refineries and factories.
It's just incredible what we're asking of them. And we haven't even touched on the fact that they have to prove these sensors aren't just making things up. There's a section on calibration that caught my eye.
Rule number 4. Calibration curves must be provided.
Right. I feel like most people trust digital displays implicitly. If the little screen says 50% humidity, well, we just assume it's exactly 50%.
And engineers know that is rarely true, especially with cheap sensors you might buy online. They drift. The students have to prove their accuracy.
How do they do that?
Well, they have to take their moisture sensor, for example, put it in bone-dry soil, and record the voltage it outputs. Then put it in completely saturated mud, record that voltage, and then they have to plot the curve in between.
So they're mathematically mapping the electrical signal to the physical reality.
It teaches them that data isn't magic. It requires validation. You can't just download a code library and hope for the best. You have to verify.
There's another requirement here that I found, well, wonderfully sadistic. It's the variation from normal conditions.
Ah, yes. The break it rule.
They have to intentionally disrupt their own system.
Yes. They have to identify 3 realistic deviations. Maybe they pour a cup of ice water into the tank to simulate a sudden freeze. Or they block the light sensor with a piece of cardboard to simulate a massive storm.
And the system has to notice. It can't just keep chugging along blindly.
It has to detect the anomaly, alert the user, maybe flash a light or sound a buzzer, and then crucially, it has to act to fix it. And the students have to record the response time.
Response time. That seems like a really critical metric here.
It is life or death for the system. I mean, if your fish tank gets contaminated with ammonia and your system takes 4 hours to filter it out, well, the fish are already dead.
Right.
The response time measurement forces them to optimize their code and their actuators for speed and power. It makes them ask, is my pump big enough? Is my sensor fast enough?
So they've built this brain, they've calibrated the eyes, they've tested the reflexes.
Yeah.
Now, where do they test it? Because this is the part that made me realize this is a serious logistical challenge. Requirement number 8.
Data logging and real-time monitoring.
Specifically, the prototype must be tested outdoors for 5 consecutive days.
Outdoors. That one word changes everything.
Why is outdoors so much harder than the classroom? I mean, a farm is outdoors, so it makes sense, but technically, what does that do to the project?
It introduces chaos, variables. In a classroom, the temperature is 22 degrees constantly. The light is fluorescent and steady. There's no wind.
But outdoors.
Outdoors, you have cloud cover passing over, changing your light readings every minute. You have wind cooling down your tank. You have the sun baking your electronics enclosure. You have the day-night cycle where temperatures might drop 15 degrees.
And rain. Let's not forget rain.
If they didn't waterproof their electronics properly, day 1 of rain just ends the project. It's over.
And they have to keep this running for 5 days straight and record data the entire time. 3 readings per parameter at fixed intervals.
This is the big data aspect. By the end of 5 days, they will have hundreds, maybe thousands of data points, and they have to process that. The document asks for graphs, error bars, and interpretation.
Error bars. I have not thought about error bars since college physics. So they aren't just plotting a pretty line. They have to calculate the statistical confidence of their own data.
It moves them from being makers to being scientists. A maker builds a cool gadget that works once. A scientist proves it works reliably, with data. The error bars show they understand the limitations of their own equipment.
There's one more software requirement that really impressed me, the database library.
Yes. The system must come preloaded with optimal settings for at least 2 different living organisms.
So I can't just hard-code my machine to grow basil and absolutely nothing else.
No, you need a menu. Imagine a user interface. You select basil, and the system automatically sets the temperature to 25 and the humidity to 60%.
Yeah, man.
Then you select spinach, and the system automatically updates the set points to, say, 18 degrees and 50% humidity.
That implies a real level of abstraction in the code. They're building a platform, not just a single-use tool.
It connects right back to the grand challenges. If Egypt or any country needs to diversify its crops, we need machines that can switch modes instantly. You don't want to build a whole new factory for every vegetable. You want a universal system that adapts.
Adaptability, that's the key. Now, I want to circle back to the physical construction. We mentioned the trash aspect at the start. The document is very strict. The body of your prototype must be constructed using recycled or waste materials.
This creates such a fascinating friction. You have these delicate, precise ceramic sensors and silicon chips, and you have to mount them on
Old PVC pipes, wooden pellets.
yogurt containers, styrofoam packaging from a new TV, discarded piping. It forces creativity, but it also forces structural engineering. How do you make a watertight seal on a 10-liter tank using an old plastic bucket and a tube of silicone?
And if that seal fails, your electronics get wet and your project is over.
And you can't just 3D print a perfect bracket. You have to scavenge. It's the MacGyver element. It teaches them that engineering isn't just about ordering the perfect part online. It's about making it work with what you have.
But there are limits to the scavenging. The ethics and safety section was pretty clear on that.
Oh, yeah. No equipment or materials belonging to the laboratories may be removed.
So you can't just raid the chemistry lab for parts.
You have to build it at school, but you have to bring your own junk. It prevents the students with better access to school resources from having an unfair advantage. Everyone has access to trash. It levels the playing field.
And there's a moral component, too, regarding the living things.
Yeah.
Humane measures should be followed when dealing with living organisms.
That's vital. We are dealing with life here. Even if it's just a goldfish or a lettuce plant, if your automation fails, something dies.
It raises the stakes. It's not just, oh, I got a B on my test. It's, I killed my fish because my loop code was too slow.
That is the burden of the engineer. It's a simulation of professional responsibility. If a civil engineer builds a bridge poorly, people get hurt. If an agricultural engineer fails, the harvest rots and people go hungry. This project simulates that. You are responsible for the life inside your machine.
And to prove they've pulled all this off, the code, the biology, the trash building, the outdoor survival, they had to make a video.
And not just some hype video, a 2 to 4 minute technical demonstration.
I noticed it specifically requires time-lapse footage of the 6-hour continuous operation.
That is the forensic proof. You can't fake a time lapse easily. If the water level drops, or the plant wilts, or the lights flicker, the camera sees it. It forces honesty. It's a full audit of the system's reliability.
It really covers the whole spectrum of skills then. You have coding, wiring, carpentry, biology, data analysis, and communication.
It's a comprehensive test of 21st century skills. You know, we talk a lot about interdisciplinary learning, but this is it. You cannot pass this project if you only know code or if you only know biology. You have to synthesize them. You have to speak both languages.
And you have to do it with a mindset of scarcity.
That might be the most important lesson for the future, I think. We are moving into a world where resources, water, energy, arable land, are becoming scarcer.
Right.
The engineers of the future won't always have unlimited budgets and brand new materials. They'll have to retrofit. They will have to optimize. They will have to make do with what is available.
That's what this project is simulating. Here is some trash. Here is a hard problem. Here is a microchip. Go save the harvest.
Exactly. It shifts the student's identity. They aren't just students taking a test. They are problem solvers. They are engineers.
It connects directly back to that first grand challenge we talked about, increasing the agricultural base.
And think about the scale. If you have 10,000 grade 11 students across Egypt building these prototypes, maybe 90% of them fail. Maybe they leak or the code crashes.
Sure.
But maybe 10% figure out a really clever way to cool a greenhouse using passive airflow and a recycled computer fan.
And that one idea could scale.
That idea could change an industry. That's the power of the Capstone. It unlocks the cognitive surplus of thousands of bright young minds and focuses them on the country's biggest problems.
It's pretty inspiring vision. It takes the terrifying problems of the world, pollution, hunger, population, and it turns them into a puzzle that can fit on a desk.
A puzzle that you solve with code, creativity, and a little bit of recycled plastic.
So at the end of the day, we have a portable, solar potential, recycled smart farm running on student-written algorithms. It's light years ahead of what I was doing in grade 11.
I was just happy if I didn't break the beaker in chemistry class.
Right. As we wrap up this deep dive,
Mm.
I think it leaves us with a really provocative thought about the rest of the world.
And what's that?
We have teenagers building self-correcting, multi-species food systems out of garbage that can survive outdoors for 5 days.
They're proving it's possible. On a small scale, but possible.
So, if a grade 11 student can do that, what excuse does industrial agriculture have for not being more sustainable? Why are our large-scale systems often so wasteful and so rigid when a student prototype can be so adaptable and efficient?
That is the question. Maybe the industry needs to go back to grade 11 and relearn how to build with purpose.
Maybe they do. Thanks for listening to The Deep Dive. We'll catch you next time.